Hello, Lucas. I'm here for my math lesson.
Come on in.
La 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 la. Hey, what are these amount one tickets for?
They're gonna be a visual aid for you. So what we're gonna learn today is why the powers of the golden ratio tend towards whole numbers as the powers get bigger. I'll explain to you what that means.
Good, because I have no idea what that is.
Okay, so the golden ratio, also known as phi, raised to some random whole power, let's go 20, it should give you about 15,126.99993389303. You know, it's close enough to a whole number.
Your average so on and so on.
Yeah. So, I'm going to show you why this is.
I can't believe you did that. You just killed the text.
We'll keep that up there as an example. So there are a few things that you're going to need to assume for this. First,
That 2 times 2 is 4.
no. First that if a over b is equal to a plus b over a, then a over b is equal to phi, the golden ratio.
Can I ask a question?
What?
Why is it called the golden ratio?
Because a lot of people kind of worship it, I guess. Anyway, let's just assume that b is equal to 1. And then we can tidy this up a bit.
Why are you killing the text?
Just go with me here.
Why are you killing the text?
We can multiply both sides by a. We have this statement here based on the definition of the golden ratio. So, and we can just get rid of those parentheses. Multiply by any power of a and see that a to the 20th is equal to a to the 19th plus a to the 18th if a is equal to phi. So phi to 1 power is equal to the sum of the 2 previous powers of phi. So,
can I ask a stupid question?
Okay.
Is phi the same thing as pi?
No. Anything to the power of 0 is 1. Anything to the power of 1 is itself.
0. Zero is equal to 1. And 1 is equal to phi?
No. Okay, so phi squared is equal to the sum of the 2 previous terms.
Snake!
What? Okay, so from here we can tell that phi to the 0 is 1, of course, and phi to the 1 is phi, and phi squared is phi plus 1, phi cubed is 2 phi plus 1, phi to the 4th is 3 phi plus 2, and so on. So, wait a minute. That sounds like the rule for Fibonacci numbers, and there are Fibonacci numbers in here as well, both what you multiply by phi and what you add on.
And I'm going to quickly say some Fibonacci numbers that I know. 1, 1, 2, 3, 5, 8,
13,
13, 21, and then, of course, after 21 comes 34.
Yep. Okay, so the next thing we're going to assume that phi times some Fibonacci number will be close to a whole number. So one way you can think about this is, say we have 8 times phi. So 8 is in the Fibonacci series, and then
1, 2, 3, 5,
8.
8. And also, 1, 1, 2, 3, 5, 8, so on and so on. And the rule for the Fibonacci number series is you always start with 1, 1, and then you add the number before it to the previous number. So that's how you get 2, and then 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on, so on.
Also, the Fibonacci numbers, their ratios tend closer and closer to phi. These are the best fractions for phi. 1 on 1. Actually, let's do bigger Fibonacci numbers. 144 on 89. Not only are these good approximations for Fibonacci numbers, but when you multiply phi by those Fibonacci numbers, you'll get the next Fibonacci number. We can tell that it will be close to the next Fibonacci number. What we can tell here is that we can just get rid of all of the things that you add on, and it'll still be as close to a whole number. And we know that when you multiply phi by a Fibonacci number, it'll be close to the next Fibonacci number. So that is why phi to any whole power will be close to a whole number. I'll see you next time. Bye!